Hey everyone, welcome back. On behalf of Forge College, I'm super excited to welcome you to another explainer in our EVM deep dive series. Today, we're unpacking something that's foundational, maybe a little intimidating at first, but honestly, utterly fascinating. We're talking about memory allocation and lifecycle. Now, if you're joining us from our previous explainer on integrating AI tools into Solana workflows, well, brace yourselves for a bit of a culture shock, right? We're pivoting away from those lightning-fast AI-driven highways of Solana, and we are stepping straight into the incredibly meticulous byte-counting workbench of Ethereum execution. Because in the EVM environment, literally every single byte matters. And more importantly, every single byte costs gas. It's kind of like moving from driving a sleek automatic sports car to meticulously assembling a mechanical Swiss watch with a pair of tiny tweezers. Okay, let's dive right into this. Here is our roadmap for today. We'll start off with a welcome to EVM memory, and then we'll introduce a really helpful core mental model, the tabletop in trays. From there, we'll look at the cost of expansion, see some of that gas math in action, explore the memory lifecycle, and finally, wrap things up with our key takeaways. All right, section 1, welcome to EVM memory, the addressable workspace. So, in previous lessons, we spent a lot of time talking about the stack, that tightly constrained last in, first out holding area for tiny, short-lived values. But what happens when you need to copy a massive chunk of cal data, or maybe build a complex payload of bytes to send over to another contract? Yeah, the stack just isn't going to cut it. You need a much larger, addressable workspace, and that is where memory comes in. Technically, memory is a contiguous byte-addressable array, meaning in your code you can ask for byte number 0 or byte number 42 specifically. But, and this is a massive but, the EVM strictly charges you in 32-byte chunks, which we call a memory word. So it literally doesn't matter if you only wanted to borrow a single byte, the EVM billing department only speaks in 32-byte increments. Moving right along to section 2, tabletop and trays, a mental model. To really get a feel for how much gas your code is going to consume, it helps to visualize your memory as a physical space. Picture a long, totally empty tabletop. Step 1, the table is completely bare. Step 2, the EVM slides a pristine tray onto the table, and we'll call that tray 0. Now this tray perfectly holds exactly 32 bytes, from offset 0 to 31. Need a little more room? Step 3, the EVM just slides in tray 1 right next to it, holding bytes 32 to 63. And this brilliantly illustrates our core rule here. You only ever expand your workspace by sliding in whole trays. So let me ask you this. What if you just need to store a single, tiny 1-byte variable? Say a little Boolean flag right at offset 0. Do you just get a cute little 1-byte coaster for your table? Nope, no way. You still have to buy the whole 32-byte tray. You write your one single byte into the first slot of tray 0, and the other 31 slots? They just sit there, completely empty, but fully paid for by you. It's absurdly strict, sure, but knowing this rule is absolutely crucial. It's like half the battle in smart contract optimization. Which brings us to section 3, cost of expansion, quadratic gas. Okay, so we know we're sliding trays onto a table, but let me introduce you to the real villain of our story here, quadratic gas costs. See, every single time you ask the EVM to slide a new tray onto the table, the restaurant bill for those trays scales quadratically. Let's break down how this rounding up behavior triggers that cost. If you have 0 bytes, that means 0 words. Your tabletop is empty, you pay absolutely nothing. But touching anywhere between 1 and 32 bytes bills you for 1 word. 33 to 64 bytes triggers that second tray, so now that's 2 words. But look at what happens at 100 bytes. 100 divided by 32 is 3.125, right? Well, the EVM doesn't do fractions, it always rounds up. So touching byte 100 actually forces you to pay for 4 full trays, securing the table all the way up to byte 127. And here is a number that should strike a healthy amount of fear, or, least respect, into any Solidity developer: 512. When the EVM calculates the incremental cost of expanding your memory, the math goes like this. It takes the square of your new word count, subtracts the square of your old word count, and then divides the whole thing by 512. Because it's squaring the total number of words, having a massive tabletop gets exponentially more expensive the longer it gets. So the crucial point is this. You've got to batch your allocations. Let's say you need 96 bytes of data. If you ask for 32 bytes, and then ask for another 32 a bit later, and then another 32 after that, well, you just triggered that nasty quadratic expansion math 3 separate times, racking up penalties all the way. But if you just compute your needs and ask for 96 bytes right up front, you only expand the table once. It's kind of like paying a one delivery fee for a giant feast rather than paying 3 separate delivery fees for individual side dishes. It just makes sense.
All right, let's see this in practice in Section 4, Gas Math in Action, a concrete scenario.
Let's treat a concrete code sequence like a receipt at a restaurant and just calculate the gas incrementally. Imagine your contract starts executing. First up, you copy 20 bytes of call data to offset 0. That touches bytes 0 to 19, so 1 tray slides in, meaning 1 word is allocated. Next, you copy 40 bytes to offset 32. This touches all the way up to byte 71, spilling over into the 3rd tray, so now you're at 3 words. Finally, an MSTORE puts 32 bytes at offset 96, and boom, that pushes you into a 4th tray. Every single one of these steps triggers a new compounding quadratic gas penalty because the EVM keeps sliding more trays onto the table. The mathematical impact of this is honestly pretty staggering. If you look at the incremental gas cost, that represents expanding memory 3 separate times, as we just did. The quadratic penalty hits you repeatedly, making it super expensive. But the batched gas cost? That represents allocating a 128-byte buffer in one single operation right at the very start. As you'll see, the batched gas cost is provably significantly cheaper. The takeaway? Plan your tabletop layout in advance for sure. Let's shift focus now. Section 5, the memory lifecycle, ephemeral scopes. So what actually happens to all these trays when the shift is over and the function finishes executing? Well, memory in the EVM is fiercely, strictly scoped to the per call frame. Think of it like a temporary pop-up workbench. Step 1, a call is initiated, and a fresh, totally blank tabletop is rolled out for you. Step 2, during execution, that memory expands as we slide our trays on. Step 3, the call returns. And step 4, that entire tabletop is aggressively and instantly wiped clean and dismantled. There's no background garbage collection slowly pausing your program. The whole workbench literally just ceases to exist. And this leads to a massive warning for developers. Return data must be explicitly copied back by the caller. Let's say contract A calls contract B. Contract B builds this beautiful entire 100-tray tabletop of memory to compute some brilliant result. But the very second contract B returns, its tabletop is thrown right in the trash. Even if you use a delegate call, a subcall's memory is totally discarded. So if contract A wants that result, it has to actively copy the return payload from the return buffer onto its own tabletop before moving on. Seriously, do not let your precious data get thrown out with the workbench. All right, let's wrap this up. Section 6, key takeaways. Operational rules. We've covered some absolutely critical engineering blueprints today, and I want to make sure these are permanently etched into your mind. Here are the core operational rules for reasoning about EVM buffers, CALDATA, or return payloads. First, memory is byte-addressable, yes, but it is billed strictly in 32-byte words. You touch a single byte, you buy the whole tray. Second, gas costs have a quadratic component. To save your users money, pre-calculate your needs and batch your allocations whenever humanly possible. And third, memory is completely ephemeral and scoped entirely to the call frame. If you want to keep the data after a subcall, you explicitly have to copy it back. Now that we've mastered this pop-up workbench, you might be wondering, what happens when we want data to live forever? Well, up next in our Ethereum Fundamentals track, we'll be diving into persistent storage structures and layout. We are going to contrast this cheap, ephemeral tabletop we just learned about with the highly permanent, incredibly expensive world of smart contract persistent storage. Trust me, you are not going to want to miss that transition. I'll leave you with this final summarizing thought. Batch your memory, mind your trays, and explicitly return your data. Living by this mantra will save you endless amounts of gas on your ephemeral tabletop. But if memory just vanishes the second your function ends, how do smart contracts actually remember your token balances forever, and at what monumental cost? Well, we'll uncover all of that in the next explainer. Thank you so much for joining me today. This explainer was proudly brought to you by Forge College. Please make sure to visit our website at forge.college to learn more about this subject and tons of other Web3 related topics. Keep exploring, keep building, and I'll see you next time.